Good morning, class. So, last lecture we have seen the selective and non-selective alpha blockers. Okay, so in the selective, we selectively block the alpha 1 blocker. They come under the selective alpha 1 blocker. In that drugs, we're having the zosin part in their structure. Okay, so prozosine, terazosin, doxazosin. So these are the selective alpha 1 blockers. Then another class of alpha 1 blocker, that is the non-selective alpha blockers. So these non-selective alpha blockers, they can bind to the alpha 1 receptor as well as the alpha 2 receptor. So they can block alpha 1 as well as alpha 2 receptor. Hence they are called as a non-selective. There is no selectivity for these drugs. So they are classified into two types, that is the reversible and irreversible. So the reversible alpha 1 blocker, these are the blockers which binds or which block the alpha receptor reversibly. That means after binding, after some time it is detaching from the receptor, then receptor can perform its function after some time. But in case irreversible alpha blocker, what happens? They are irreversible. That means once they bind to the receptor, it is difficult for them to detach from the receptor. So they consider the irreversible. Why irreversible blocker? It is formed. It is due to the formation of covalent bond between the drug and the receptor. So already we have seen in case of irreversible like phenoxybenzamine. So in the phenoxybenzamine, they are having the structure what we have seen in the nitrogen mustard, that is the haloalkyl amine like structure. So here you can observe this type of structure, that is the haloalkyl amine structure. So if these structures are present, they undergo release of Cl minus, so it forms a azidinium ion. And this azidinium ions, it looks for the nucleophile and it binds to the nucleophile. Here the nucleophile is the receptor. So it binds to the nucleophile and it forms a covalent bond. And due to the formation of this covalent bond, this bond cannot be detached from the receptor. So it permanently blocks that receptor. That means for the long time the reaction can be takes place. So generally once we are giving the dose of this, it can show the activity for 3 to 4 days. Okay, so this is about the irreversible blockers. Okay, so that we have seen in the last lecture. Then we have seen how the metabolism of adrenaline, noradrenaline, dopamine takes place. Actually, dopamine we have seen in the antiparkinsonian. For next study, we have seen the synthesis of dopamine, noradrenaline, and adrenaline. Along with that, we have seen the metabolism of these one. Okay, so they are synthesized from the amino acids. So phenylalanine to the tyrosine, from tyrosine to the dopa is synthesized, from dopa to the dopamine, from dopamine it is synthesized noradrenaline, and then adrenaline is synthesized. So that is the pathway for the synthesis of adrenaline and noradrenaline. Then these compounds, they undergo the metabolism, and they undergo metabolism due to the presence of catechol nucleus. That is the one benzene ring. It has two hydroxy groups which are nearer to the each other. So that catechol nucleus is prone for the metabolism. So they are generally undergo metabolism by two enzymes. One is the COMT and another one is the MAO, that is the monoamine oxidase and catecholomethyl transferase. So this COMT, it causes the hydroxy group to convert into the methoxy group, and this monoamine oxidase enzyme, it causes oxidation of amine group. Hence the penultimate carbon, it converted into the acid. So that is the process which takes place during the metabolism of adrenaline and noradrenaline. And finally they are converted into the mandelic acid derivative. So that is the pathway that we have seen yesterday, that is how the synthesis of dopamine takes place, adrenaline takes place, noradrenaline, and how the metabolism takes place with the help of enzyme COMT, that is the catecholomethyl transferase, and another one is the MAO, that is the monoamine oxidase. Okay, now we are moving to the next and important part, that is the beta blockers. So yesterday we have seen the alpha blockers. Now we are moving to the next part, that is the beta blockers. So these are the drugs which binds to the receptor, that is the beta receptor, and they block the activity of adrenaline or noradrenaline present on the beta receptor. So the such drugs, they consider the beta blockers. So these beta blockers, so during the investigation or during the research, they found that these beta blockers, these drugs, they having a similar kind of structure what we have seen in case of adrenergic agonist. So आपण adrenergic agonist बघितलेला, त्याचा SAR बघितलाय. So researchers they found that the structure of these adrenergic agents and these beta blockers, they are nearly the same, or we have to modify the some of the structure which is present in the agonist so that it will give the antagonist. So what is the structure of agonist? So we have seen, so in the agonist we have seen there is one benzene ring is there, then here amine is there, it is attached to the alkyl group, and here hydroxy group is there, and here 2 hydroxy group is there. So this is the alpha carbon, this is beta carbon. So on the beta carbon there is a hydroxy group, and on the benzene ring there are 2 hydroxy groups are present. So these 2 hydroxy groups, they are nothing but the makes them the cortical nucleus. So this is the structure of the adrenergic agents. Okay, now the scientists they told that we have to modify some part of this structure to get the antagonist effect or to get the antagonist drug. So what are the modifications? So we have to replace these 2 hydroxy groups. आपल्याला हे 2 hydroxy group रिप्लेस करायचे आहेत. सो कशाने रिप्लेस करायचे? वी कॅन रिप्लेस इट विथ SO2NH2 ग्रुप. यातला एक हायड्रॉक्सी ग्रुप काढायचा, तिथं SO2NH2 ग्रुप ऍड करायचा आणि दुसरा CH2OH. Okay, so we can replace one of the hydroxy group by the SO2NH2 and another by the CH2OH. So it becomes the antagonist. Or second thing is what we have to do, we have to replace only one hydroxy group and we have to remove this hydroxy group. So that can be a second possibility to form a antagonist. Okay, so one, we have to replace one of the hydroxy group with the SO2NH2 and CH2OH, or we have to remove one of the hydroxy group, so it becomes the antagonist. That is the first part. Then second, this part it is necessary for the antagonist activity also. हा जो मधला part आहे, that is the this carbon along with this hydroxy group. So this part is necessary or it is required for the activity. Then next part, this R, that is the substitution which is present on the terminal amine group, it should be the larger group so that it becomes the antagonist. So these are the some modifications we can done to form a antagonist from the agonist structure. So it is found that the antagonist drug or the beta blockers, they having the similar kind of structure what we can see in the adrenergic agents. It is the agonist. We have to modify some of the parts of this agonist, and after modifying the part of the agonist, like 2 hydroxy group, if one of the hydroxy group, we will convert it into the SO2NH2 or into the CH2OH, and if we remove the another hydroxy group, that is the one condition. Second one, the middle part, CH2 along with the hydroxy group, this middle part is necessary for the activity. And finally the R which is present or the substitution on the terminal amine group, that R, this R must be a higher group or it having the larger group so that it produces the antagonist effect. So महत्वाचे काय, cortical nucleus मधले 2 hydroxy group ते रिमूव्ह करायचे, and second one जो R group आहे, जो substitution आहे तो bulkier करायचा, जो large group करायचा, so that it can becomes the antagonist. So this is the some modifications we can perform. After modifying this one, the drug can be converted into the antagonist effect. Okay, so this is some introductory part. Now the next part we can go for the middle part. So what we have seen, the at the center there must be presence of 2 carbons and hydroxy group, but there are some modifications at the central part. If we modify this part, then it can be drastically increase the antagonist activity of a drug. Okay, so what is the general structure for the beta blockers? I will tell you. Aromatic group, then X, then CHOH, then CH2, has CH2 ला NH group, and finally this R group. So this is the general structure for the beta blockers, or the beta blocker drugs can be derived from this type of structure. Okay, so first part, this aromatic group, it be devoid of hydroxy groups. There must be no hydroxy group. So that aromatic group we can add SO2NH2 group, or we can add CH2H group. Second part, this R group is the bulkier group, so we can add this R group as a bulkier group or the larger group. So when we have that larger group or the bulkier group, the drug becomes antagonist. And then main important part, what we have seen, the middle part, it remain as it is. Okay, so one we can add, that is the X group we can add in between. हा X आहे तो आपण aromatic group आणि मधली जी अल्किल चेन आहे त्यामध्ये आपण इंट्रोड्यूस करू शकतो. So that X can be hydrogen, that X it can be OCH2 group. तो X काय असेल, एक तर हायड्रोजन असेल किंवा तो X काय असेल, OCH2 group असेल. So from that group, the beta blockers, they are classified into two types. That is the first one, if X having H, X ला जर H असेल तर काय होईल, this is aryl group, this is CH2 means ethyl group, hydroxy means ethanol, and this is amine. So X is hydrogen, so what will be the nomenclature of the drug? Aryl, ethanol, amine. Aryl, this is ethanol with hydroxy group, and this is amine. So aryl, ethanol, amine derivatives. That is the one class of a beta blocker. Second one, if X is OCH2, what will be happen? Okay, OCH2 आहे, X हा OCH2 आहे आणि हा ह्याला जॉईन केला. सो ArOCH2 CH2NH. So असं जर असेल, what will be the group or what will be the nomenclature? So aryl oxy आणि हे 1 2 3 propanol amine. Are you getting my point? If OCH2 group we attach, then it becomes aryl oxy propanol amine. So that is the another class of beta blockers. So beta blockers, or the structure of beta blockers, they are generally classified into two parts. That is the one when X having the hydrogen, and another one when X having the OCH2 group or the methoxy group. So from that they are classified into two types. Suppose X is the hydrogen, so what it becomes? Aryl ethanol amine. Okay, and if the X is the OCH2, then drug becomes aryl oxy propanol amine. So that is the two different classes of beta blockers which are present. So are you getting my point? Beta blockers, they are similar kind of structure of adrenergic agent. What is the modification? दोन जे हायड्रॉक्सी ग्रुप असतात ते दोन हायड्रॉक्सी ग्रुप ते रिमूव्ह केलेले आहे. त्यापैकी एक हायड्रॉक्सी ग्रुप काढून तिथं SO2NH2 करू शकतो किंवा CH2H काढू शकतो, किंवा एक हायड्रॉक्सी ग्रुप आहे तो आपण पूर्णपणे रिमूव्ह करू शकतो. आणि नेक्स्ट पार्ट, दॅट इज द जे टर्मिनल ग्रुप आहे किंवा टर्मिनलला जो आर ग्रुप आहे, तो टर्मिनल आर ग्रुप आपण काय करू शकतो, बल्की ग्रुप अटॅच करू शकतो. मोठा ग्रुप ब्युटाइल, pentyl, like this group we can attach, and if such groups can attach, then drug becomes antagonist. And सगळ्यात ड्रास्टिकली चेंज कधी होतो, तर सगळ्यात ड्रास्टिकली बीटा ब्लॉकर्स आपल्याला कधी मिळणार, when CH2 or the methoxy group is attached. हा ग्रुप जेव्हा आपण X म्हणून in between insert करतो, त्यावेळी drug becomes aryl oxy propanol amine, and which is the काय आहे, it is the drug which having a drastically increase in the antagonist activity as compared to the other antagonists. हे जर केलं तर त्याच्या ऍक्टिव्हिटी मध्ये एकदम ड्रास्टिक चेंज होतो, ऍक्टिव्हिटी एकदम जास्त प्रमाणात वाढते. ओके, सो दिस इज अबाउट द basic information regarding the beta blockers. Okay, So now check the structure of beta blocker. So please go through the structure. They having the two chlorines instead of hydroxy group. Okay, remaining all structure is same. फक्त काय हायड्रॉक्सी ग्रुप दोन काढलेले आहेत. So due to replacement of two hydroxy group by the chlorine group, the drug becomes antagonist. So this dichloroisoproterenol is the first drug invented which having some kind of antagonist activity. But during research they found that this drug is partial agonist. So they can produce uh, some kind of agonist activity also. So that drug is not come into the market, or it is not marketed drug. So the research has been done on this drug, and from this drug another drugs are invented. But dichloroisoproterenol and what we have seen, that is the adrenergic agonist, that is the isoproterenol. Isoproterenol मध्ये काय असतं, दोन क्लोरीनच्या ऐवजी इथे दोन हायड्रॉक्सी ग्रुप अटॅच केले, it becomes isoproterenol. But this isoproterenol is a agonist drug, and if we replace two hydroxy group by two chlorine, remaining all the structure is same, the drug becomes dichloroisoproterenol. So this dichloroisoproterenol is a antagonist, but it has some kind of agonist activity. So it is the partial agonist. So it is difficult to uh, give into the market as a antagonist agents, because they may cause increase in the tension also, that is the blood pressure. So it may cause the hypertension as the side effects. Hence this drug is not uh, approved by the US FDA. So after study they found that if the benzene ring, that is this benzene ring, if we convert it into the naphthyl ring, it is the two benzene ring which is fused with each other, that is the naphthyl ring. So they found that if we convert the benzene ring into the naphthyl ring, then we will got a drug, and that drug, that is the pronethelol. So that is the drug which is invented, which having a similar kind of structure like dichloroisoproterenol. Only the removal of chlorine takes place, and instead of that chlorine we are attaching the another benzene ring to the fused benzene rings, two benzene rings. So it is called as pronethelol with the naphthyl ring. Then another example is cytolol. So in that drug all the structure is similar, only one benzene ring, and here there is a presence of CH3CONH2. ओके. सो इथं जे दोन हायड्रॉक्सी ग्रुप असतात त्यापैकी एक हायड्रॉक्सी ग्रुप काढायचा, आणि इथं ग्रुप कुठला असतो, CH3SOONH. So that group is present at this position, and the drug becomes cytolol. ओके. सो सगळ्या ड्रगचं स्ट्रक्चर जवळपास सेम आहे. ओके. सो isoproterenol, that is the agonist drug. So they having the, instead of Cl, two hydroxy groups are present. Then dichloroisoproterenol, chlorine groups. If we fuse this ring into benzene ring, then it becomes pronethelol. And in this ring, if this chlorine is not present, and here there is a presence of CH3CO2NH group, the drug becomes sotalol. Okay. So in this way, we can modify in the structure, and from modification we can find out a best suitable antagonist which can produce the antagonist effect, which can be used as the antihypertensive agent. So until now we have seen what are the modifications we can done in the antinergic agonist so that the drug becomes the beta antagonist. Okay, so in that modification, the aryl group, in the aryl group or in the catechol nucleus, we have to remove the two hydroxy groups, and with the hydroxy group we can add another chlorine groups or CH3SO2 or the OCH2 groups. So such groups we can add by removing the hydroxy groups. Then in case of the X, that is the linkage between the aryl group and the ethylamine chain or ethanolamine chain. In that X, the X may be the H or X may be the OCH2. If X is H, then the drug becomes aryl ethanol amine or aryl ethanolamine derivatives. If X is OCH2, then the drug becomes aryl oxy propanol amine and their derivative. Then it is found that the aryl group which is present at the one side, that aryl group, it can be replaced by the naphthyl ring or the naphthalene ring. It can be replaced by the heterocyclic ring. So it will not produce such changes in the effect, or it will not reduce the effect of the drug. Okay, so that aryl group can be the para-substituted aryl group or benzene ring, or it may be the naphthalene ring, it may be the heterocyclic ring. Okay, so such changes we can make, then the drug becomes antagonist. And generally, if we have the OCH2 group, that is the aryl oxy propanolamine chain, then the drug becomes more antagonist as compared to the X is equal to H. Okay, so detail regarding the SAR we will see. So these are some examples what we have seen as the beta blockers. So here you can observe this hydroxy group, they are replaced by the 2Cl, but it becomes the partial agonist, so this drug is not clinically used. And here you can find out one naphthalene ring is present in the form of allyl ring pronethalol, so it is the beta blocker. So this is, and in the propranolol you can see that there is OCH2 group. Okay, so propranolol is more active as compared to the pronethalol because it having the OCH2 group as the X instead of it having the hydrogen as the X, what we can see in the pronethalol. Okay, so this is about some basic information regarding the beta blockers. So now we will move to the next part, that is the SAR of beta blockers. Okay, so most of the beta blockers, they are chemical class of aryl oxy propanol amine. So what we have discussed, this is aryl group, this is OCH2 group, so it becomes aryl oxy. So there are three carbons are there, it becomes propane, and due to the alcohol it is propanol, and this is amine. So aryl oxy propanol amine, it is the basic nucleus which is having the more potent antagonist activity as compared to the other agents, that is the here if hydrogen is present. Okay, now the two carbon chains are essential for the activity what we have seen, and the secondary amine having the optimum activity. Now during going for the SAR, so this aryl group already we have discussed, it should not have the two hydroxy groups. So these are two hydroxy group, it can be replaced by the methyl sulfonamide group or OCH2 group, or absence of one of the hydroxy group, it can be produced as the antagonist effect. Then these two groups, that is the CH2 CH2, it was for the activity. If these two groups are present, that is the two carbon chains, they are essential for the activity. And finally it is the secondary amine. So most of the drugs you find out the R is, that is the structure becomes NH CH, here CH3, here CH. So that is the secondary amine. So if secondary amine is present, the drug show the optimum activity. If we are replacing this hydrogen with any other group like CH3 or CH5, though it becomes the tertiary amine, so this activity will reduce, or drug becomes inactive. So if we are replacing this hydrogen or secondary amine by any other higher alkyls, so the activity will be reduced or the drug becomes completely inactive. So the configuration of hydroxy group. So here you can find out if this hydroxy group is present, this hydroxy group is a chiral center. So this part is different, here different, one hydroxy group, here hydrogen. So this carbon which having the hydroxy group, this carbon, so due to the chiral center it shows the different isomers. Okay, so this group or this carbon plays an important role in the beta antagonist activity, that is the blocking the beta receptor. If the carbon possesses S configuration, then there is optimal activity for the beta receptor, and if it is S configuration, the drug becomes 100 times more potent as compared to the S configured compound. For example, they have given the propranolol. So this propranolol is having R configuration, and this is S configuration. So S configuration having optimum effectivity, so it is 100 times more potent. So this S isomer is 100 times more potent as compared to the R propranolol. So most lipophilic beta blockers, they can enter into the central nervous system than less lipophilic drugs. So they will cause more serious side effects. So drugs like propranolol, drugs like labetalol, they're having the higher lipophilicity, so they can produce as the CNS side effects. So these drugs having the higher lipophilicity, these having the intermediate lipophilicity, that is the metoprolol, bisoprolol, carvedilol, and the drugs like sotalol, nidolol, atenolol, these having the low lipophilicity, or they are generally said to be the hydrophilic beta blockers. Then presence of amide group at para position. So here you can observe the amide group at the para position. Then it will retain the activity for beta 1 selectivity. So the atenolol, labetalol, these structures they having the amide group at the para position. So they will have the selectivity activity for the beta 1 receptor. Okay. Now in brief the SAR of beta antagonist we have to see. So regarding the aryl group, so aryl group is required to determine the beta receptor blocking potency. That is, it is beta 1 selective or beta 2 selectivity. If they having the two halogen atoms, then it produces the partial agonist. If it having the aryl group, it has the heterocyclic ring or it having the naphthalene ring, it will show the better antagonist activity. Then this carbon is a chiral center. In case of chiral center, the drug becomes highly stereoselective. Then this is secondary amine. In the secondary amine, if hydrogen is replaced with any other higher alkyls like CH2, CH3, CH2, CH3, at that time the drug becomes less active or drug becomes inactive. Okay, so these are some important parts regarding the SR of beta receptor antagonist. So aryl group, it must be lacking two hydroxy groups or catechol nucleus. Instead of that, the aryl group may having the benzene ring with the para substitution like CH3SO2NH2 or OCH3 CH2OH substitution, or it may lack one hydroxy group, or it may be the heterocyclic ring, or it may have the naphthalene ring. Then at the center there is the presence of two or three carbon atoms. Generally two carbon atoms are necessary to show the activity. In case of the carbon which is having the hydroxy group, it shows the chiral center, so it shows the stereoselective compounds. It shows the different isomers, one of which having greater activity as compared to another one. Finally, we have the amine group, which is the secondary amine. If this secondary amine, if we convert it into tertiary amine by replacing hydrogen with any other alkyl group, then it will inactive the compounds or it will decreases the compound. Then important part, this carbon number must be the 3 to 4. If we are more increasing the number of carbon, then the antagonist activity will decrease. Then this carbon, it can be present in the cyclic form or it can be present in the open chain form, but it should be the secondary amine, it should not be the tertiary amine. Okay, so these are some important points regarding the SAR of beta receptor antagonist. Then we will move to the next part. From introduction to the beta blocker and their structures, we are moving to the next part, that is the classification of beta blockers. So these beta blockers are classified into two types, that is the selective or non-selective. So like alpha blockers, the selective beta blockers are the drugs which can bind to the beta 1 receptor and show the beta 1 blocking activity. While there are some drugs which can bind to the beta 1 receptor as well as the beta 2 receptor, such drugs considered as non-selective. And there are some drugs which can be alpha as well as the beta blocker, that is the mixed antagonist. Such drugs, they are the labetalol and carvedilol. So the cardioselective drugs which act on the beta 1 receptor, these are the drugs which are the cardioselective or beta 1 receptor antagonists. These are the four drugs which come under the non-selective agents. And these are the labetalol and carvedilol. These are the agents which are the mixed antagonists. That is, they can act on the alpha receptor as well as the beta receptor. So just write down the structures of the drugs. So sotalolol, pindolol, propranolol, timolol. These are the non-selective agents. So sotalol is the non-selective. Here you can find out to the aryl group at the para position there is a CH3 SO2 NH is present, so it produces the antagonist effect. In case of acetylbutalol, there is a amide linkage is present which is required for the selectivity or the beta selectivity. Similar in case of smolol. Smolol is also the beta 1 selective drugs. Draw the structures of sotalol, acetylbutalol, and smolol. Please draw the structure. These are the beta 1 blockers. Okay, so the sotalol is the non-selective beta blockers, so they can block beta 1 receptor as well as the beta receptor. While this one, that is acetylbutalol, smolol, these are the non-selective, so that means they can act on beta 1. They are selective, sorry, they are the beta 1 selective, they act only on beta 1 receptor. These are the other beta blockers. Propranolol, this is the structure of propranolol, so it is aryl ethanol amine structure. So it is pronitrol. This is structure of propranolol. This is the naphthyl ring. It having the O methoxy group. This ring, it decreases the selectivity of the propranolol, while this group, it is required to bind to the beta receptor. Then timolol, this group, that is the butyl group, it indicates the beta 2 receptor selectivity. These groups are required for the blockage activity. Then metoprolol, write down the structure. Atenolol, butoxolol. Okay, so we will stop here. So today's lecture, what we have seen the general structure of beta blockers, how the modification can be done in the adrenergic agonist drug, so that the drug becomes antagonist, that we have seen. Then we have seen some examples of beta blockers. Then we have seen the classification of beta blockers, in that the selective beta blockers and non-selective beta blockers. Selective means they can particularly bind to the beta 1 receptor or beta 2 receptor. Non-selective means they can bind to the beta receptor, that is beta 1 as well as the beta 2 receptor. So there are two drugs, that is the carvedilol and labetalol. These are called as mixed antagonists. That means they can block to the alpha receptor as well as the beta receptor. So in this way, the classification of the beta receptor takes place. Then we have seen some examples of beta blockers with their structure. Okay, so detailed study regarding the SAR of beta blockers. So how the modification of adrenergic agents, adrenergic agonist agents to the drugs like pronetholol, and from drugs like pronetholol, how it will converted into the propranolol, then how it converted into the beta selective drugs. So what are the modifications we have to done so that drug becomes more beta selective? So such modifications, such changes that we will see in the next lecture. So the detail regarding the SAR as well as the modifications to increase its selectivity or decrease the selectivity, that we will see in the next lecture. Okay, so we will stop here.